Have you ever looked up at the night sky and wondered how far we could actually go? Not just in theory, not in science fiction, but in physical reality, bound by the laws that govern everything in existence. When we think about space travel, we often imagine distant galaxies, alien worlds, and humanity spreading across the cosmos. But there's a hard boundary out there, an absolute wall that no amount of technology, ingenuity, or determination can break through. This isn't about what we haven't figured out yet. This is about what the universe itself forbids. Right now, in this moment, light from distant galaxies is racing away from us. And no matter how fast we build our ships, no matter how clever our engines become, we will never catch it. There are places in the universe that are already beyond our reach, not because we lack the means, but because the fabric of space itself is moving faster than anything can travel through it. Before we explore why, if you find this topic as fascinating as I do, consider subscribing and leaving a like. It helps more people discover these ideas. Now, let's understand the absolute limit of human travel through space. When we talk about traveling through space, we first need to understand what space actually is. For most of human history, space was thought to be an empty stage, a fixed background where matter and energy performed their cosmic dance. But space is not empty, and it is not fixed. Space itself is a physical thing, a fabric that can bend, stretch, and expand. This understanding came from Albert Einstein's general theory of relativity, published in 1915, which describes gravity not as a force pulling objects together, but as the curvature of space-time caused by mass and energy. This theory has been tested thousands of times through observations of planetary orbits, the bending of starlight around massive objects, the precise timing of signals from satellites, and the detection of gravitational waves from colliding black holes. Every test confirms that space is dynamic, responsive to the matter and energy within it. The expansion of space was discovered through careful observation of distant galaxies. In the 1920s, astronomer Edwin Hubble measured the light coming from galaxies beyond our own. He noticed something peculiar. The light from these galaxies was shifted toward the red end of the spectrum, a phenomenon called redshift. This redshift occurs because the wavelengths of light are stretched as space itself expands. The farther away a galaxy is, the more its light is redshifted, which means the faster it appears to be moving away from us. This relationship between distance and recession speed is known as Hubble's law, and it provided the first concrete evidence that the universe is expanding. Hubble's observations were made using the 100-inch telescope at Mount Wilson Observatory, measuring the brightness and spectral lines of stars in distant galaxies. His work built on earlier theoretical predictions by Georges Lemaitre and observations by Vesto Slipher, creating a consistent picture of an expanding universe. This expansion is not galaxies moving through space like ships through an ocean. It is space itself stretching, carrying galaxies along with it. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move apart, not because they are traveling across the rubber, but because the rubber between them is expanding. Galaxies behave the same way. They are embedded in space, and as space expands, the distance between galaxies increases. This expansion happens everywhere simultaneously. Between every pair of galaxies not bound together by gravity, space is stretching. The rate of this expansion is described by the Hubble constant, a number that tells us how fast space is expanding per unit of distance. Current measurements place this value at approximately 70 km per second per megaparsec, though there is ongoing research to refine this number. A megaparsec is roughly 3.26 million light-years, so for every 3.26 million light-years of distance, space expands by about 70 km per second. Now, here's where the absolute limit begins to appear. Because space itself is expanding, distant objects can recede from us faster than the speed of light. This might sound like it violates Einstein's rule that nothing can move through space faster than light, but it doesn't. Einstein's speed limit applies to objects moving through space, not to space itself. Space can expand at any rate. There is no law preventing it from stretching faster than light can cross it. This means there are galaxies right now that are moving away from us faster than light. Not because they are traveling through space at such speeds, but because the space between us and them is expanding so rapidly that the total recession velocity exceeds the speed of light. The speed of light in a vacuum is approximately 299,792 km per second. This speed is not arbitrary. It emerges from the fundamental structure of spacetime itself, from the relationship between electric and magnetic fields described by Maxwell's equations. Every experiment ever conducted, from measurements of light travel time between Earth and the Moon using laser reflectors, to observations of particle behavior in accelerators, to the synchronization of atomic clocks on fast-moving aircraft, confirms that this speed is absolute and unchangeable for anything moving through space. Light does not experience time. From the perspective of a photon, if it could have a perspective, its emission and absorption occur in the same instant. This is because as an object approaches the speed of light, time slows down relative to a stationary observer, an effect called time dilation, which has been measured countless times using precise atomic clocks and fast-moving particles. For objects with mass, reaching the speed of light is impossible. As something accelerates closer to light speed, its relativistic mass increases, meaning it takes more and more energy to accelerate it further. To actually reach the speed of light would require infinite energy, which is not available in any finite system. This isn't a technological limitation. It's a fundamental property of the universe. Particle accelerators like the Large Hadron Collider accelerate protons to 99.999990% the speed of light, and the energy required to push them even slightly faster grows exponentially. These particles have been measured with extraordinary precision, and their behavior matches exactly what relativity predicts. There is no wiggle room here, no loophole we might exploit with better technology. So we have established that nothing can travel through space faster than light, and that space itself can expand at any rate. This combination creates a boundary called the cosmological horizon, sometimes known as the Hubble horizon or the cosmic light horizon. This is the distance beyond which objects are receding from us faster than light due to the expansion of space. Currently, this boundary lies at roughly 14 billion light-years away, though the exact value depends on how we measure cosmic distances and the expansion rate. Any galaxy beyond this horizon is moving away from us faster than light can travel through space. Light emitted from such a galaxy, even though it travels toward us at the speed of light through space, is actually losing ground because space itself is expanding faster in the opposite direction. It's like trying to walk forward on a treadmill that's moving backward faster than you can walk. You move forward relative to the treadmill belt, but you travel backward relative to the room. Here is where the absolute limit becomes clear. If we wanted to travel to a galaxy beyond the cosmological horizon, we would face an impossible task. Even if we could build a ship that travels at the speed of light, which we cannot, we would never reach that galaxy. The space between us and it is expanding faster than we can cross it. We would be like someone running on an ever-lengthening track where the finish line moves away faster than we can run. But the situation is actually worse than this. The expansion of space is not constant. It is accelerating. This acceleration was discovered in 1998 by two independent teams of astronomers studying distant supernovae. They measured the brightness and redshift of Type I supernovae, which serve as standard candles because they all explode with roughly the same intrinsic brightness. By comparing how bright these supernovae appear to how bright they should be based on their redshift, astronomers could determine how far away they are and how fast the universe was expanding at different times in the past. What they found was unexpected. The universe's expansion is not slowing down due to gravity pulling everything together, as many had assumed. Instead, it is speeding up. Distant supernovae were dimmer than expected, meaning they were farther away than they should be if the expansion rate were constant or decreasing. This discovery earned the Nobel Prize in Physics in 2011 and introduced us to one of the deepest mysteries in cosmology: dark energy. Dark energy is the name we give to whatever is causing this acceleration. We do not know what it is. We cannot see it directly. We can only observe its effect on the expansion of space. Current measurements suggest that dark energy makes up roughly 68% of the total energy content of the universe, with dark matter making up about 27% and ordinary matter, everything we can see and touch, making up just 5%. The leading model for dark energy is the cosmological constant, a term Einstein originally introduced into his equations and later called his greatest blunder when the expansion of the universe was discovered. The cosmological constant represents a baseline energy density inherent to empty space itself, a kind of vacuum energy that remains constant even as space expands. If this model is correct, then every cubic meter of space contains a small amount of energy, And as space expands, more cubic meters are created, leading to more total energy and faster expansion. This creates a runaway effect. The more space expands, the more dark energy there is, which causes space to expand even faster. Observations of the cosmic microwave background radiation, the leftover light from the early universe measured with extraordinary precision by satellites like COBE, WMAP, and Planck, support the cosmological constant model, though other explanations remain possible. Because the expansion is accelerating, the cosmological horizon is not static. Over time, more and more galaxies will cross this boundary and become unreachable. Right now, we can still see light from galaxies beyond the current horizon because that light was emitted when those galaxies were closer to us, before the expansion carried them beyond the reachable limit. But if we wait too long, even the light from these galaxies will become so redshifted that it fades into undetectability, and new light they emit will never reach us. There is a future point, billions of years from now, when most of the galaxies we can currently observe will have disappeared beyond the horizon. Observers in that distant future will see a much emptier universe, with only the galaxies in our local gravitational cluster remaining visible. This brings us to the concept of the observable universe versus the reachable universe. The observable universe is the sphere of space from which light has had time to reach us since the beginning of the universe roughly 13.8 billion years ago. Due to the expansion of space, this sphere is currently about 46 billion light-years in radius, even though the universe is only 13.8 billion years old. This happens because the space light traveled through expanded while the light was in transit, increasing the total distance. But the reachable universe, the volume of space we could actually travel to, is much smaller. It is limited not by how far light has traveled, but by the expansion rate of space itself. Calculating the exact boundary of the reachable universe requires understanding the future evolution of cosmic expansion, which depends on the properties of dark energy. If dark energy remains constant, as the cosmological constant model suggests, then the reachable universe extends to roughly 18 billion light-years from Earth. Any galaxy currently farther than this will eventually cross the cosmological horizon and become unreachable, even by light. Any galaxy currently closer than this could, in theory, be reached by a traveler moving at nearly the speed of light, though the journey would take an extraordinary amount of time. But there's a critical detail here. Even if a galaxy is currently within the reachable zone, the longer we wait to begin the journey, the farther away it becomes due to expansion. Every moment we delay, the distance increases. For some galaxies near the boundary, there is a deadline, a point beyond which no journey, no matter how fast, can ever reach them. Let's consider what it would take to travel to a galaxy within the reachable universe. Suppose we identify a galaxy 10 billion light-years away, well within the 18 billion light-year boundary. If we launched a spacecraft today traveling at 99% the speed of light, it would take just over 10 billion years of Earth time to reach that galaxy if space were not expanding. But space is expanding, and accelerating, so the galaxy is moving away from us during the entire journey. By the time we arrive, if we can arrive, billions more years may have passed, and the galaxy may have moved significantly farther from Earth. For the travelers on board, time dilation would make the journey seem shorter, but for anyone remaining on Earth, or for anyone observing the journey from an external reference frame, the travel time would stretch far beyond the initial distance in light years. Now consider the practical challenges of such a journey. Accelerating a spacecraft to 99% the speed of light requires enormous amounts of energy. The kinetic energy of an object is given by the relativistic formula, which accounts for the increase in mass as speed increases. For a spacecraft with a mass of, say, 1,000 kilograms, accelerating it to 99% the speed of light would require energy equivalent to several times the total annual energy consumption of human civilization. And that's just to get it up to speed. Slowing down at the destination requires the same amount of energy again. There are theoretical propulsion systems that could, in principle, achieve such speeds. The Bussard ramjet, proposed in 1960 by physicist Robert Bussard, would use magnetic fields to scoop up hydrogen from the interstellar medium and fuse it for propulsion. Theoretical calculations suggest this could work, but the engineering challenges are immense, including creating magnetic fields strong enough to collect sufficient fuel and dealing with the radiation produced by constant fusion reactions. Another concept is the photon rocket, which would use the momentum of light itself for propulsion. Since photons carry momentum, directing a powerful beam of light backward would push the spacecraft forward. The problem is efficiency. Photon rockets have extremely low thrust compared to the energy they consume. To achieve high speeds, the rocket would need to carry an enormous amount of fuel, which increases its mass, which in turn requires more fuel. This is the tyranny of the rocket equation, first formulated by Konstantin Tsiolkovsky in 1897. The equation shows that the final speed of a rocket depends on the exhaust velocity of its propellant, and the ratio of its initial mass to its final mass. To reach relativistic speeds, the mass ratio would need to be astronomical, far beyond what any known materials or designs could achieve. Antimatter propulsion offers better energy efficiency. When matter and antimatter collide, they annihilate completely, converting their entire mass into energy according to Einstein's famous equation E equals mc squared. This is the most energy-dense reaction possible. A single kilogram of antimatter reacting with a kilogram of matter would release roughly 9 times 10 to the 16th joules of energy, equivalent to several thousand nuclear bombs. In theory, this could propel a spacecraft to significant fractions of light speed. The problem is producing and storing antimatter. Currently, we can create tiny amounts of antimatter in particle accelerators, measured in nanograms, at enormous cost and energy expenditure. Storing it requires magnetic or electric containment fields to prevent it from touching ordinary matter and annihilating. No practical method exists for producing antimatter in the quantities needed for interstellar propulsion. Even if we solve propulsion, there are other obstacles. At high speeds, even tiny particles become dangerous projectiles. A single grain of dust, a speck of ice, or a stray hydrogen atom, hitting a spacecraft traveling at 99% the speed of light would release kinetic energy equivalent to a small bomb. The interstellar medium, the space between stars, is not empty. It contains roughly 1 hydrogen atom per cubic centimeter on average, along with occasional larger dust grains. At relativistic speeds, these particles would constantly bombard the spacecraft, eroding its hull and exposing its interior to radiation. Shielding would help, but the shield itself would gradually erode and would add mass to the spacecraft, requiring more energy to accelerate. Some designs propose using magnetic fields to deflect charged particles, but this only works for ions and electrons, not for neutral atoms or dust grains. Radiation is another serious concern. Cosmic rays, high-energy particles from supernovae and other energetic events, constantly stream through space. At rest, Earth's magnetic field and atmosphere protect us from most of this radiation. In deep space, shielding becomes critical. But as a spacecraft accelerates to relativistic speeds, an effect called the relativistic beaming occurs. The cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space with a temperature of roughly 2.7 Kelvin, becomes blue-shifted and concentrated in the direction of travel. At 99% the speed of light, this radiation would appear to come from straight ahead with energies comparable to X-rays or gamma rays, intense enough to damage electronics and harm biological tissue. Additional shielding would add more mass, worsening the propulsion challenge. Then there's the issue of navigation and communication. At relativistic speeds, time dilation means time passes more slowly for the travelers than for those left behind. A journey that takes 50 years of ship time might correspond to thousands of years of Earth time, depending on the speed and distance. Communication would become increasingly delayed. A message sent from the ship to Earth would take years or centuries to arrive, and by the time a response came back, the ship might have already completed its journey or encountered unforeseen problems. This makes real-time problem-solving impossible. The crew would need to be entirely self-sufficient, capable of handling any emergency without outside help. The human body presents additional challenges. Extended exposure to microgravity causes bone density loss, muscle atrophy, fluid redistribution, and vision problems due to increased intracranial pressure. Long-duration space travel would require artificial gravity, likely generated by rotating the spacecraft to create centrifugal force. The structure would need to be large enough that the rotation doesn't cause disorienting Coriolis effects. Then there's psychological stress. The isolation, confinement, and distance from Earth would be profound. Studies of Antarctic research stations, submarines, and the International Space Station provide some insight into how humans cope with isolation, but an interstellar journey would be far more extreme. The crew would know they are traveling into a future they cannot return to, with everyone they knew on Earth long dead by the time they arrive. Despite all these challenges, none of them represent absolute physical limits. They are engineering problems, extraordinarily difficult ones, but not violations of known physics. The absolute limit comes not from these practical obstacles, but from the expansion of space itself. No matter how advanced our technology becomes, we cannot outrun the expansion of space beyond the cosmological horizon. This is not a matter of insufficient energy or clever engineering. It is a fundamental boundary imposed by the structure of space-time. To understand why this boundary is absolute, we need to look at the equations governing cosmic expansion. The expansion rate of the universe is described by the Friedmann equations, derived from Einstein's general relativity. These equations relate the expansion rate, the energy density of the universe, and the curvature of space. Observations tell us the universe is very close to flat, meaning its curvature is approximately zero, and that its energy content is dominated by dark energy with a roughly constant density. Plugging these values into the Friedmann equations gives us the scale factor, a quantity that describes how the size of the universe changes over time. When the scale factor is increasing, space is expanding. When it's accelerating, the expansion is speeding up. The key insight is that the scale factor's acceleration creates a horizon. Beyond a certain distance, the recession velocity of distant objects exceeds the speed of light. This horizon is not a physical barrier, not a wall you would crash into. It's a boundary of reachability. As you approach it, you would never perceive anything unusual locally. Space around you would seem normal. But the galaxy you're trying to reach would always remain ahead of you, receding faster than you can close the distance. You could travel at 99.9999% the speed of light, and it wouldn't matter. The space between you and your target is growing faster than you can shrink it. This is different from simply being far away. If space were not expanding, given enough time and speed, any distance could be crossed. But with accelerating expansion, some distances are growing faster than light can cross them, and that growth rate is itself increasing. There is no speed you can achieve, no amount of time you can wait, that will allow you to cross this boundary. You are racing against something that has no speed limit, and that grows stronger as you struggle against it. Now let's consider the implications for the future of human space travel. Our local group of galaxies, including the Milky Way, Andromeda, and about 50 smaller galaxies, is bound together by gravity. These galaxies are close enough that their mutual gravitational attraction overcomes the expansion of space. They will eventually merge into a single large galaxy over the next few billion years. The expansion of space has no effect on systems bound by gravity, whether that's planets orbiting stars, stars orbiting in galaxies, or galaxies bound in clusters. So within our local group, space travel remains possible in principle, limited only by the vast distances and the engineering challenges discussed earlier. But beyond the local group, nearly every other galaxy is receding due to expansion. The nearest large galaxy cluster outside our local group, the Virgo cluster, is roughly 50 million light-years away and receding. It is still within the reachable universe, but barely, and the window for reaching it is closing. Every year we delay, the journey becomes longer. There will come a time, in the cosmologically near future, when the Virgo cluster crosses the boundary and becomes unreachable forever. This pattern repeats for every distant structure in the universe. Galaxies, galaxy clusters, superclusters, all of them are slipping beyond our reach. If the cosmological constant model of dark energy is correct, this process will continue indefinitely. The universe will keep expanding, accelerating, carrying distant structures farther and farther away. Eventually, trillions of years from now, The night sky as seen from Earth, or from wherever our descendants might be, will be empty except for the merged remnant of the local group. Every other galaxy will have receded beyond the cosmological horizon, their light stretched to undetectable wavelengths. Future civilizations, if any exist, will have no direct evidence that the universe is larger than their local cluster. They will not be able to observe the cosmic microwave background, the expansion of space, or any of the evidence that led us to understand cosmology. Their universe will appear static and finite. This future is often called the Big Freeze or heat death, a state where the universe continues expanding forever, matter becomes increasingly diffuse, stars burn out, and eventually even black holes evaporate through Hawking radiation. But long before that, long before the last stars die, the era of cosmic exploration will have ended. The reachable universe will have shrunk to just our local surroundings. This raises a philosophical point. The universe is vast, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, and likely an uncountable number of planets. Yet the overwhelming majority of this universe is and always will be beyond our reach. We can observe it, study it through telescopes, learn about its structure and history, but we cannot go there. There is a fundamental asymmetry between observation and interaction. Light from distant galaxies can reach us, carrying information, but we cannot send anything back that will ever arrive. Some have proposed theoretical ways around this limit, but none are grounded in experimentally verified physics. Wormholes, hypothetical tunnels through spacetime that could connect distant regions, are solutions to Einstein's equations, but they require exotic matter with negative energy density to remain stable. No such matter has ever been observed or created in a laboratory, and quantum field theory suggests it may not be possible to accumulate enough of it to hold a wormhole open. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, would warp spacetime around a spacecraft, contracting space in front and expanding it behind, allowing faster-than-light travel without violating relativity. But this design also requires exotic matter in enormous quantities, and it raises questions about causality, the ability to send signals to your own past, which creates logical paradoxes. Even if such exotic propulsion methods were possible, they wouldn't change the fundamental limit imposed by the accelerating expansion of space. A wormhole could theoretically connect 2 points in space, but if those points are receding from each other faster than light due to expansion, maintaining the connection would require continuously adding energy to counteract the expansion, and the amount of energy needed would grow without bound. The Alcubierre drive might allow local faster-than-light travel, but it would still be traveling through expanding space. Once you cross the cosmological horizon, you are in a region of space receding faster than light, and no amount of local warping can overcome that global expansion. There's another subtle point here about the definition of distance in an expanding universe. When we say a galaxy is 10 billion light-years away, we have to specify what we mean by that distance. There's the comoving distance, which accounts for the expansion of space and represents the distance the galaxy would be if we could freeze the expansion right now and measure a straight line. There's the light travel distance, which is how far light from that galaxy has actually traveled through space, less than the comoving distance because space was smaller in the past when the light was emitted. And there's the angular diameter distance, the proper distance at the time the light was emitted, which can actually decrease for very distant objects due to the peculiarities of expansion. When we talk about the reachable universe, we're talking about comoving distance, the actual separation accounting for expansion. This is the distance that determines whether we can physically get there. The mathematics of cosmic expansion also reveals something subtle about the cosmological horizon. It is not fixed in space. As the universe expands, the horizon itself moves outward, but galaxies move away even faster. Imagine standing at the edge of a river where the current flows faster than you can swim. Even though the riverbank behind you is moving away, you are being carried downstream faster than the bank recedes. The horizon is like that riverbank, always receding, but you're being swept away faster than it moves. This also means there are galaxies that are currently beyond the horizon but whose light, emitted long ago when they were closer, is still reaching us. We can see them, study them, measure their properties, but we can never visit them. And eventually, their light will become so redshifted that even that information flow will cease. The observable universe and the reachable universe are different things, and both are shrinking in terms of the number of independent structures we can interact with. There's a certain tragedy in this realization. We live in a special time, cosmologically speaking. We can observe the cosmic microwave background, the afterglow of the Big Bang, which tells us about the early universe. We can see distant galaxies in various stages of evolution, allowing us to reconstruct the history of cosmic structure formation. We can measure the expansion rate and infer the existence of dark energy. Future civilizations, if they arise billions of years from now, will not have access to this information. The evidence will have literally moved beyond their reach. They will live in a universe that appears static and small, with no way to learn about its true nature. We are living in the era when the universe is most knowable, most observable, and also, paradoxically, when the limits on what we can reach are beginning to close in. Now let's address a common question. If space is expanding everywhere, why don't we expand with it? Why don't atoms, planets, and galaxies grow larger as space stretches? The answer is that expansion only occurs where there are no other forces to counteract it. Within atoms, electromagnetic forces hold electrons to nuclei. Within solid matter, chemical bonds hold atoms together. Within the solar system, gravity holds planets in orbit. Within galaxies, gravity keeps stars bound. All of these forces are enormously stronger than the gentle stretching of space. It's only over vast distances, where no bound structures exist and where the cumulative effect of expansion adds up, that we observe recession. The space between galaxy clusters expands because there's nothing holding them together. But the space within a galaxy does not expand in any measurable way because gravity dominates. There is a subtle effect called cosmic expansion's influence on orbital dynamics, but it is vanishingly small. The expansion of space contributes a tiny outward acceleration to objects in orbit, but this acceleration is so weak that it is completely negligible compared to gravitational forces for any bound system. For example, the expansion of space contributes an outward acceleration to Earth's orbit around the Sun that is roughly 20 orders of magnitude smaller than the Sun's gravitational pull. It is utterly unmeasurable and has no practical effect. Only over distances of millions of light years, where no single gravitational source dominates, does expansion become significant. This brings us to an interesting thought experiment. Suppose we could build a chain of space stations, each one separated by, say, 1,000,000 kilometers, stretching from Earth all the way to a distant galaxy billions of light years away. If we built this chain right now, maintaining the links between each station, what would happen as space expands? The answer is that the chain would stretch. The links would be pulled apart by the expansion of space. To keep the chain intact, we would need to constantly add energy to push the stations back together, fighting against the expansion. The farther out the chain extends, the more energy we would need. For a chain stretching to a galaxy near the cosmological horizon, the energy required to maintain the links would exceed the total energy content of the observable universe. And if the galaxy is beyond the horizon, no amount of energy could keep the chain intact. The expansion would win. This thought experiment illustrates why the horizon is absolute. You cannot build a bridge across it, cannot lay a cable, cannot establish any physical connection. The universe itself, the expansion of space-time, severs any such connection. This is not a limitation of materials or engineering. It is a limitation imposed by the structure of reality. Now, let's consider what we do know we can reach. The moon is roughly 384,000 kilometers away. We've been there. Mars, at its closest approach, is about 55 million kilometers away. We've sent robotic missions. The outer planets, Jupiter, Saturn, Uranus, Neptune, are billions of kilometers away, but within reach of our current technology. Voyager 1, launched in 1977, is now more than 23 billion kilometers from Earth, still sending back data. It has entered interstellar space, the region beyond the influence of the Sun's solar wind, but it is still gravitationally bound to the Sun, moving in a very elongated orbit. At its current speed of roughly 17 kilometers per second, it would take over 70,000 years to reach the nearest star, Proxima Centauri, if it were headed in that direction, which it is not. Proxima Centauri is 4.24 light-years away, about 40 trillion kilometers. With current propulsion technology, reaching it in a human lifetime is impossible. But it is not beyond the absolute limit. It is within the Milky Way, bound by gravity, not receding due to expansion. In principle, if we could accelerate a spacecraft to a significant fraction of light speed, we could reach it. The engineering challenges are immense, but the physics allows it. The nearest large galaxy, Andromeda, is about 2.5 million light-years away. It is actually moving toward us, not away, because the mutual gravity between the Milky Way and Andromeda overcomes local expansion. In roughly 4 billion years, the two galaxies will collide and merge. Traveling to Andromeda would take millions of years even at near light speed, and the time dilation effects would mean that anyone making the journey would arrive in a distant future where Earth's civilization might no longer exist in any recognizable form. But again, it is not beyond the absolute limit. It is reachable, at least in principle. Beyond the local group, things change. The Virgo cluster, the nearest large cluster of galaxies, is receding. It is still within the reachable universe, but the journey would need to begin relatively soon on cosmic timescales. Waiting too long means the distance grows insurmountable. And beyond the Virgo cluster, the vast majority of galaxies, clusters, and superclusters are already too far. They are beyond the boundary where the expansion of space exceeds the speed of light. They are observable, their light reaches us, but we can never go there. This leads to a final question. Could there be a way to stop or reverse the expansion of space? Could we somehow alter the properties of dark energy, prevent the acceleration, and bring distant galaxies back within reach? The answer, as far as we know, is no. Dark energy is not something we can manipulate. It is a property of space itself, or a field permeating space, and it operates on cosmological scales. Even if we could somehow inject enormous amounts of energy or matter into a region of space, the effect would be localized and temporary. The global expansion of the universe is driven by the total energy content of all of space, and our ability to influence that is negligible. We are, in a very real sense, passengers on the surface of an expanding balloon, unable to stop the balloon from inflating. Some speculative theories suggest that dark energy might change over time, that the acceleration might slow or even reverse, leading to a big crunch where the universe collapses back on itself. If that were to happen, the cosmological horizon would shift, and galaxies currently beyond reach might become reachable again. But current observations provide no evidence for this. The acceleration appears steady, consistent with a cosmological constant. If dark energy is truly constant, then the expansion will continue accelerating forever, and the reachable universe will continue to shrink. There's a concept in cosmology called the particle horizon, which is the boundary of the observable universe, the farthest distance from which light has had time to reach us. This is different from the cosmological horizon, which is the boundary of the reachable universe. The particle horizon is currently about 46 billion light-years away, while the cosmological horizon is about 14 billion light-years away. Everything within the particle horizon but beyond the cosmological horizon is visible but unreachable. We can see it, but we can never get there. This asymmetry is fundamental. Information can flow inward across the cosmological horizon, carried by light and other radiation, but nothing can flow outward across it. It is a one-way membrane in space-time. This also means that there is information we can never access. If there are civilizations, planets, or phenomena beyond the cosmological horizon, we will never know about them unless their light, emitted when they were closer, happens to reach us. And if such light exists, it carries information only about the distant past of those objects, not their current state. Anything happening right now beyond the horizon is permanently hidden from us. The universe is larger than the part we can observe, and even larger than the part we can ever hope to explore. So here is the absolute limit. The reachable universe is finite. It is bounded by the accelerating expansion of space. No improvement in technology, no increase in energy, No clever manipulation of physics can change this. There are places we will never go, not because we lack the means, but because the universe itself forbids it. Space is expanding faster than light can cross it, and that expansion is accelerating. The boundary is closing in, not in the sense that our local region is shrinking, but in the sense that the number of independent structures, galaxies, clusters, that we can reach is decreasing over time. Every moment we wait, more of the cosmos slips beyond the horizon. This is not a reason for despair. We live in a universe vast beyond comprehension, filled with wonders, mysteries, and opportunities for exploration. The Milky Way alone contains hundreds of billions of stars, many with planets, some potentially harboring life. The local group contains enough galaxies to explore for millions of years. The reachable universe, though finite, is still unimaginably large. But it is important to understand the limits, to recognize that there are boundaries imposed not by our technology or willpower, but by the fundamental nature of reality. Space is not a passive backdrop. It is an active, dynamic fabric that expands, curves, and shapes the possibilities of existence. And that expansion creates an absolute limit on human travel through space, a horizon beyond which we can never venture, no matter what we do. If you've found this exploration of cosmic limits thought-provoking, consider subscribing to see more content that examines the boundaries of what's possible in our universe. The absolute limit of space travel is not a failure of imagination. It is a profound truth about the universe we inhabit, a reminder that reality imposes constraints even on our greatest ambitions. Understanding these constraints doesn't diminish the adventure of exploration. It sharpens it, focusing our attention on what is possible, on the vast regions of space that remain within reach, waiting to be discovered. The implications of this limit extend into questions about the long-term future of any civilization, not just humanity. If intelligent life exists elsewhere in the universe, and evidence suggests the conditions for life may be common given the abundance of planets and habitable zones around stars, then every such civilization faces the same boundary. They too are confined to their local gravitational neighborhood. They too watch as distant galaxies slip beyond reach. This means the universe is not headed toward a future where different civilizations eventually meet, explore each other's territories, or share the cosmos. Instead, the universe is fragmenting into isolated islands, each containing a cluster of gravitationally bound galaxies, with no possibility of contact between islands. This fragmentation has been studied through computer simulations that model the future evolution of cosmic structure. These simulations take the observed properties of the universe, the density of matter and dark energy, the current expansion rate, and project forward billions of years. What they show is consistent across different models. Galaxy clusters that are not currently gravitationally bound will lose contact with each other. The space between them will expand to such a degree that no signal, no spacecraft, no information of any kind can cross from one cluster to another. Each cluster becomes its own isolated universe, causally disconnected from all others. Within a cluster, normal physics applies. Stars form, planets orbit, civilizations could potentially rise and explore. But beyond the cluster, there is only an ever-expanding void. The timescale for this isolation depends on the properties of dark energy. If dark energy remains constant, as current evidence suggests, then the isolation process will take tens of billions of years to complete. Galaxies currently within the reachable universe will gradually slip beyond the horizon. The night sky will slowly empty. But if dark energy somehow increases in strength over time, a possibility called phantom energy, the process could accelerate dramatically. In some phantom energy models, the expansion becomes so extreme that it eventually tears apart gravitationally bound structures. First galaxy clusters would dissolve, then individual galaxies, then solar systems, then planets, and eventually even atoms would be ripped apart in an event called the Big Rip. Current observations do not favor this scenario, but they cannot completely rule it out. The nature of dark energy remains one of the most important unsolved problems in physics. Understanding the absolute limit also changes how we think about the search for extraterrestrial intelligence. Projects like SETI, the search for extraterrestrial intelligence, scan the sky for radio signals or other signs of technological civilizations. The assumption has always been that if such civilizations exist, and if they are trying to communicate, their signals would travel through space and eventually reach us. This is true for civilizations within our local region of the universe. Radio waves, like all electromagnetic radiation, travel at the speed of light. A civilization 1,000 light-years away could send a signal that reaches us 1,000 years later. We could potentially detect it, send a reply, and establish communication, albeit with a very long delay between messages. But for civilizations beyond the cosmological horizon, communication is impossible. Even if they sent a signal toward us, that signal would be caught in the expansion of space. It would travel toward us at the speed of light through space, but the space itself would be expanding faster in the opposite direction. The signal would lose ground, its wavelength stretching, its energy decreasing, never reaching us. And any signal we sent toward them would suffer the same fate. This means there could be countless civilizations in the universe, some perhaps far more advanced than humanity, and we will never know they exist. They are beyond the absolute limit of contact. This raises a philosophical question about the meaning of existence in an isolated universe. If there are parts of the universe that can never interact with our part, in what sense do they exist for us? Physicists and philosophers have debated this question. Some argue that existence is objective, that those distant regions exist regardless of whether we can observe or reach them. Others suggest that operationally, things we cannot interact with in any way, even in principle, might as well not exist from our perspective. This is not solipsism, the idea that only one's own mind is sure to exist. It is a recognition that the universe naturally divides into causally disconnected regions, and that statements about regions beyond our causal horizon cannot be tested or verified. General relativity, the theory that describes spacetime and gravity, is built on the principle that physics should be local. The laws of physics at any point in space depend only on the conditions at that point and in its immediate vicinity. Information propagates at finite speed, the speed of light, so distant events cannot instantly affect local conditions. This locality is fundamental to how the universe operates. The cosmological horizon is an extension of this principle. Beyond the horizon, events occur that have no causal influence on us. They cannot send us signals, cannot affect our experiments, cannot alter our observations. In a very real sense, they are outside our universe, even though they are part of the larger cosmos. This also affects how we interpret cosmological measurements. When we measure the properties of the universe, the density of dark energy, the expansion rate, the distribution of galaxies, we are measuring our local region. We assume these properties are the same everywhere because the universe appears homogeneous and isotropic on large scales. Homogeneous means it looks the same at every location. Isotropic means it looks the same in every direction. Observations of the cosmic microwave background radiation strongly support this assumption. The temperature of this radiation is remarkably uniform across the entire sky, varying by only about 1 part in 100,000. This uniformity suggests the universe is very similar everywhere, at least within the observable region. But we cannot directly test whether the universe beyond the cosmological horizon has the same properties. It could be different. The density of dark energy could vary from region to region. The expansion rate could differ. The laws of physics, in principle, might not be identical everywhere, though there is no evidence or theoretical reason to think they change. This uncertainty is unavoidable. The absolute limit means there are things we cannot know, questions we cannot answer through observation or experiment. We must accept that some aspects of the universe are forever beyond our reach, both physically and epistemologically. Despite this, cosmology has made extraordinary progress by focusing on what can be observed and measured. The cosmic microwave background radiation, discovered accidentally in 1965 by Arno Penzias and Robert Wilson, has been mapped with increasing precision by a series of satellite missions. The most recent, the Planck satellite, measured temperature fluctuations in this radiation to a precision of a few parts per million. These fluctuations, tiny variations in temperature across the sky, are the seeds of all cosmic structure. Regions that were slightly denser in the early universe had slightly warmer radiation. Gravity amplified these density differences over billions of years, pulling matter together to form the first stars, galaxies, and galaxy clusters. By analyzing the pattern of these fluctuations, cosmologists can determine the age of the universe, the density of different types of matter and energy, and the geometry of space. The results are consistent across multiple independent measurements. The universe is 13.8 billion years old, give or take a few tens of millions of years. It is spatially flat, meaning parallel lines remain parallel over cosmic distances, at least within the observable region. It contains roughly 5% ordinary matter, the stuff of atoms, planets, and stars. Roughly 27% is dark matter, an unknown form of matter that interacts through gravity but not through electromagnetism, making it invisible to telescopes. And roughly 68% is dark energy, the mysterious component driving the accelerated expansion. These numbers come from combining measurements of the cosmic microwave background with observations of distant supernovae, the distribution of galaxies, and the effects of gravitational lensing, where massive objects bend light from more distant sources. Each of these measurement techniques provides an independent check on the others, and the fact that they agree gives us confidence that the model is correct, at least within the observable universe. But the model also makes predictions about regions we cannot observe. It predicts that the universe is much larger than the observable portion, possibly infinite. If space is flat and the universe began with the Big Bang, then it is likely infinite in extent, stretching forever in all directions. But if so, most of that infinite universe is beyond the cosmological horizon, unreachable and unobservable. We can infer its existence through theory and extrapolation, but we cannot verify it directly. This brings us back to the question of what we can actually do with the universe that is accessible to us. The Milky Way galaxy, our home, is roughly 100,000 light-years across and contains between 200 billion and 400 billion stars. The number is uncertain because many stars are faint, hidden by dust, or located in the dense core where observations are difficult. Each star is a potential system of planets. NASA's Kepler mission, which operated from 2009 to 2018, discovered thousands of exoplanets by measuring the tiny dips in starlight when a planet passes in front of its star. Analysis of Kepler data suggests that roughly half of Sun-like stars have at least one planet in the habitable zone, the region where temperatures allow liquid water to exist on a planet's surface. If this ratio holds across the galaxy, there could be tens of billions of potentially habitable planets in the Milky Way alone. Exploring even a tiny fraction of these worlds would take millions of years with current technology, and far longer if we include travel time at sublight speeds. But unlike galaxies beyond the cosmological horizon, these stars and planets are reachable in principle. There is no fundamental barrier preventing us from eventually visiting them, only the practical challenges of propulsion, life support, and time. Projects like Breakthrough Starshot, announced in 2016, propose using powerful lasers to accelerate tiny spacecraft to 20% the speed of light. These spacecraft would be little more than microchips with sails, weighing just a few grams, propelled by light pressure from ground-based lasers. At that speed, they could reach Proxima Centauri in about 20 years, sending back images and data via laser communication. This is at the edge of current technological capability, requiring advances in materials, laser systems, and miniaturization, but nothing about the concept violates known physics. Scaling this up to crewed missions is far more difficult. Humans require life support, shielding, living space, and artificial gravity. A spacecraft large enough to carry people would need vastly more energy to accelerate, and would take much longer to reach even nearby stars. Generation ships, spacecraft designed to support multiple generations of crew during centuries-long voyages, have been proposed since the early days of spaceflight. The challenges include maintaining a closed-loop ecosystem where air, water, and food are continuously recycled, preventing genetic bottlenecks in a small population, and ensuring social stability over timescales far longer than any human institution has ever lasted. But again, these are engineering and social challenges, not absolute physical limits. The same cannot be said for travel beyond the cosmological horizon. No generation ship, no matter how well designed or long-lived, can reach a galaxy receding faster than light. No propulsion system, no matter how efficient, can overcome the expansion of space itself. This is why the cosmological horizon represents an absolute limit in a way that interstellar distances within the Milky Way do not. Interstellar travel is hard, perhaps prohibitively so with current technology, but it is possible in principle. Intergalactic travel to distant clusters is impossible, not because it is hard, but because the universe forbids it. Some have pointed out that the existence of this limit depends on our current understanding of physics, and that future discoveries might reveal new possibilities. This is true in a narrow sense. If general relativity is wrong, or incomplete, then the predictions about cosmic expansion could change. But general relativity has been tested extensively, and has passed every test with extraordinary precision. The predictions of gravitational time dilation have been confirmed using atomic clocks at different altitudes and velocities. The precession of Mercury's orbit, unexplained by Newtonian gravity, matches Einstein's predictions exactly. Gravitational waves, ripples in spacetime predicted by the theory, were directly detected by LIGO in 2015, opening a new window on the universe. The theory's description of black holes has been confirmed through observations of stars orbiting the supermassive black hole at the center of the Milky Way and through the imaging of the event horizon shadow of the black hole in the galaxy M87 by the Event Horizon Telescope. Any new theory of gravity would have to reproduce all of these successes while also explaining new phenomena. It would have to reduce to general relativity in the regimes where general relativity has been tested. This constrains how different a new theory could be. It is unlikely that a future theory would eliminate the cosmological horizon entirely, though it might shift its location or change the details of how it behaves. The fundamental reason the horizon exists, the expansion of space, is supported by so much evidence that abandoning it would require overturning nearly a century of observational cosmology. Similarly, the speed of light limit is deeply embedded in the structure of spacetime as described by special relativity. This theory has been tested even more extensively than general relativity. Particle accelerators routinely accelerate subatomic particles to velocities exceeding 99.99% the speed of light, and the particles behave exactly as relativity predicts. Time dilation has been measured using unstable particles called muons, which are created when cosmic rays strike the atmosphere. These muons decay with a known half-life. At rest, they would decay before reaching the ground, but when traveling at relativistic speeds, time dilation extends their lifespan, allowing them to reach detectors at sea level. The number of muons detected matches the predictions of relativity precisely. GPS satellites provide another everyday confirmation. The clocks on GPS satellites run slightly faster than clocks on Earth's surface because they are higher in Earth's gravitational field, experiencing less gravitational time dilation, and slightly slower because they are moving, experiencing more kinetic time dilation. Both effects are predicted by relativity, and both must be accounted for in GPS calculations. Without these corrections, GPS coordinates would drift by several kilometers per day. Every time someone uses GPS to navigate, they are implicitly confirming the predictions of relativity. Given this weight of evidence, it is reasonable to conclude that the speed of light is a true limit and that the cosmological horizon is a real boundary. Future discoveries might reveal subtleties or exceptions in extreme conditions, but they are unlikely to overturn the basic framework. We must accept that there are parts of the universe we will never reach, not because of technological limitations, but because of the way spacetime itself is structured. This acceptance does not mean resignation or abandonment of exploration. It means understanding the scope of what is possible and directing our efforts accordingly. The reachable universe is still vast. The Milky Way offers countless destinations. The local group, including Andromeda and dozens of smaller galaxies, will remain accessible for billions of years. Even some nearby galaxy clusters, like Virgo, might be reachable if we act on sufficiently long timescales. The question is whether humanity, or any civilization, can sustain the focus, resources, and stability needed for such long-term projects. History suggests this is difficult. Human civilizations have risen and fallen over timescales of centuries or millennia. Projects like building the pyramids or cathedrals span multiple generations, but interstellar voyages would span hundreds or thousands of generations. Maintaining continuity of purpose over such periods requires social structures and technologies we have not yet developed. It requires solving not just the physics and engineering of spaceflight, but also the challenges of governance, resource allocation, cultural transmission, and long-term thinking. These are not impossible problems, but they are formidable ones. There is also the question of motivation. Why would a civilization invest enormous resources in sending missions to distant stars when the travelers would never return and the benefits, if any, would accrue to distant descendants? One answer is curiosity, the desire to explore and understand. This has driven human exploration throughout history, from early seafaring voyages to the space race. Another answer is survival. If Earth becomes uninhabitable due to asteroid impact, climate change, or other catastrophes, having colonies elsewhere ensures the continuation of the species. But colonizing nearby planets like Mars or moons like Europa might provide sufficient redundancy without requiring interstellar travel. The cost-benefit calculation is not obvious. Yet despite these uncertainties, the fundamental fact remains. There is a hard limit on how far we can go, imposed not by lack of ambition or technology, but by the structure of the universe itself. This limit is moving. Every moment that passes, more of the universe slips beyond reach. We live in a universe that is actively closing doors, erasing possibilities, shrinking the realm of what can ever be explored. This process is slow on human timescales, imperceptible in a single lifetime, or even 1,000 lifetimes, but inexorable on cosmic timescales. Understanding this limit changes the context of human existence. We are not living in a universe where expansion outward is unlimited, where the cosmos is an infinite frontier waiting to be claimed. We are living in a universe with boundaries, where the accessible region is finite and shrinking. This does not diminish the value of exploration or the wonder of the cosmos. If anything, it makes the universe we can reach more precious, more worthy of attention and care. We have a limited window, cosmically speaking, to explore beyond our local neighborhood. Once that window closes, it closes forever. This perspective also highlights the importance of the present moment in cosmic history. We live roughly 14 billion years after the Big Bang, in an era when the universe is still young enough that distant galaxies are observable, when the cosmic microwave background is still detectable, when the evidence of the universe's origin and evolution is still accessible. Future civilizations, billions of years from now, will not have this access. They will live in a darker, emptier universe, with fewer clues about the cosmos's nature. In this sense, we are privileged. We exist at a time when the universe is maximally knowable, when the most information is available, when the greatest range of phenomena can be observed. This privilege comes with a responsibility, not a moral responsibility imposed from outside, but a practical one arising from circumstance. If we do not learn what we can about the universe now, while the evidence is available, that knowledge may be lost forever. Future generations may not have the opportunity to discover what we can discover today. This makes scientific investigation urgent in a way that transcends immediate practical applications. We are documenting the universe, gathering data that might be the only record of cosmic phenomena for all future time. The absolute limit of human travel through space is also a reminder of the universe's indifference. The cosmos does not care about our ambitions, our curiosity, or our survival. It operates according to laws that have no regard for human desires. Space expands not because it wants to, but because that is what the equations of general relativity, combined with the properties of dark energy, dictate. There is no malice in this expansion, but also no accommodation. The universe is not hostile to life, but neither is it friendly. It simply is, unfolding according to physical law, creating conditions that sometimes allow complexity and consciousness to emerge, but offering no guarantee of their persistence or spread. This indifference is both sobering and liberating. It is sobering because it strips away any illusion that the universe is designed for us, that we are special in some cosmic sense, or that exploration will necessarily succeed. It is liberating because it places the responsibility for our future entirely in our hands. There is no destiny, no predetermined path, no cosmic purpose we must fulfill. We are free to choose our goals, to decide what is worth pursuing, to create meaning in an indifferent universe. The absolute limit exists, but within that limit, vast possibilities remain open. If we choose to explore, we must do so with clear understanding of what is possible and what is not. We cannot reach most of the universe. We cannot escape the cosmological horizon. We cannot reverse the expansion of space or prevent distant galaxies from receding. But we can explore our local region. We can study nearby stars, visit neighboring planets, perhaps even establish outposts in other solar systems. We can continue to observe the distant universe, learning from the light that reaches us, even if we cannot visit its source. We can ask questions, conduct experiments, and refine our understanding of how reality works. The act of exploration is valuable not only for what it discovers, but for what it represents. It is an assertion that knowledge matters, that understanding is worth pursuing, that the universe is worth investigating even when practical benefits are unclear. This is not naivety or romanticism. It is a recognition that curiosity is fundamental to what makes us human, or indeed, what makes any intelligence meaningful. A mind that does not seek to understand its surroundings, that does not push against the boundaries of the known, is not fully realizing its potential. The absolute limit of human travel through space defines those boundaries with unusual clarity. It is not a fuzzy horizon that might be pushed back with better technology. It is a sharp line drawn by the universe itself, beyond which we cannot pass. Knowing where that line is, understanding why it exists, and accepting its reality are essential steps in navigating our cosmic future. We can rage against the limit, deny it, or ignore it, but it will not move. Or we can acknowledge it, focus our efforts on what lies within reach, and make the most of the universe we can access. In the end, the absolute limit is not a story of limitation alone. It is also a story of what the universe is, how it works, and where we fit within it. We are patterns of matter and energy, briefly organized into structures complex enough to contemplate their own existence, located in a small corner of an immense, expanding cosmos. Most of that cosmos is beyond our reach, moving away from us faster than light, driven by forces we are only beginning to understand. But the part we can reach, the stars we can observe, the questions we can ask, and the answers we can find, are enough. They have to be. Because they are all we have, and all we will ever have. The universe sets the limits. Within those limits, we choose what to do,